So we can start. Felipe, the floor is yours.
Sure. Yeah, no, thank you so much, Giovanna, and thanks also to for RisingWave for having invited me. And since today's webinar is basically about RisingWave and ScyllaDB, I thought it would be a good idea for me to start basically to give you guys about an introduction about what ScyllaDB is. So what I'm going to do now is to share my screen, and you guys can see it?
Mm-hmm.
Yeah, oh good. Yeah, so I'll try to be as quick as possible and brief as possible because I know Tao today is going to basically cover the technical nuggets. But yeah, so I do have many slides to go through as well, so I'll try to go as brief as possible. And before I actually explain to you guys what ScyllaDB is, I typically like to, provide some context on why the world needs another database, right? We already have too many databases in the world, so why another? And one of the things that I particularly like about joining you guys from RisingWave today is that basically we are here actually trying to address the very same set of challenges. So RisingWave is doing a truly impressive job on, addressing stream processing scaling challenges, just like ScyllaDB is doing the same, but as a NoSQL OLTP database. So no wonder that ScyllaDB and RisingWave typically share a common group of use cases. And you may be wondering, what are some of those challenges? Well, if you are here, then you probably know, and you might be facing a few of them already. So you may need to process massive amounts of data. You need fast response times. You can't afford latency spikes. You don't want to deal with the burden of scaling your infrastructure all the time. And perhaps the most important motivation behind all this, you also want to keep your costs under control, right? So why do we need yet another database? Well, basically because the existing ones we have are not enough. For example, if I talk about relational databases, we know that they can only deal with structured data, and after a certain tipping point, they won't easily scale. If we talk about MongoDB, for example, MongoDB is really nice and easy for us to get started. It allows you to store data in an unstructured way. But we all know that when it comes to top-notch performance, especially if you have a write-heavy workload, very heavy data ingestion, MongoDB performance isn't so great. We then have solutions like caches, and here the example is actually Redis. And I love caches. Guys, they are super fast, but unfortunately, unless you have the budget, you can't store an entire data set in memory. And not every workload out there can work as a simple key value store. And then we get to the last group of databases, which are like Apache Cassandra, DynamoDB, or Bigtable. And those databases, they're reasonable. They have great high availability. They support a rich set of data types. But as you scale, you will end up with either an insane deployment, which will be too hard or complex for you to manage, or it will cost you a fortune. So here's our proposal. What if we had everything in one? We want a database which doesn't cost an arm and a leg for our business. We also want it to be fast, even at high throughputs. It should be reasonably simple to manage because, again, we don't want to manage hundreds or thousands of nodes clusters because this is sort of madness. And we also don't want to, reinvent the wheel. I mean, there are too many databases already. And it should be reasonably easy for us to get started and to use this database, given the knowledge we from other databases we already worked with. So to summarize, guys, we want a database which is built for predictable performance at scale. So what do I mean by predictable performance at scale? By predictable, I mean a database that can be almost as fast as a cache. In this slide, on the left-hand side, we see main cache D serving 3 million reads per second. On the right-hand side, ScyllaDB is serving almost the same 3 million rows per second, and the latency is in microseconds. What do we mean by performance? Well, basically the ability to overcome today's and tomorrow's engineering challenges with fairly easy. ScyllaDB was the first database in the world to process 1 billion rows per second. This is impressive, right? But do you know what's more impressive? We actually did that 5 years ago, back in 2019. And what do we mean by at scale? Well, by at scale, I mean, you need a database which is able to sustain your workloads no matter what scale you are currently running at. Like Discord, which migrated from Apache Cassandra to ScyllaDB to store trillions of messages with 60% infrastructure savings and better latencies. So, millions, billions, trillions, no matter what scale you're at, we from ScyllaDB, we promise you the best performance out there. So you may be wondering, okay, that is interesting, but how do you guys actually do this? Because if you go to any database website, every single database is probably going to claim they are the fastest one in the world, right? But what ScyllaDB has of which is different from other databases? So the first thing is that ScyllaDB is a database which is built from the ground up with performance in mind. And I probably could spend lots of time just on this slide alone, but what I want you to really understand when you think about ScyllaDB is that basically what we did is we applied low-level programming concepts, which we brought from operating systems and the Linux kernel, and we transported those concepts to the world of databases. For example, before ScyllaDB, we invented the KVM hypervisor. So if you ever worked with virtualization technologies, then you know that KVM is today used by Google Cloud and AWS. So what are some of the interesting architecture concepts in ScyllaDB? ScyllaDB follows what we call, wait for it, a fully asynchronous shard per core, shared nothing architecture. And yes, that's a big name, and you guys can see that even I have trouble pronouncing it. And to explain to you what it is, I needed to break it down in smaller pieces. ScyllaDB is fully asynchronous because we never block. All database operations rely on future and promises, in turn allowing you to maximize your infrastructure power. Shard per core means ScyllaDB shards your data on a pure CPU basis. For example, in the picture here at the top, we can see that each CPU is a different shard for your data. And finally, we get to shared nothing, which means that each CPU or each shard gets an exclusive and dedicated amount of system resources. All these concepts unified allow ScyllaDB to scale beyond what typical databases can and deliver consistent low latency, even at high throughputs, maximizing the ability of modern infrastructure. So, is ScyllaDB just fast? Do we have anything to offer to the world beyond just performance? Because performance is important, but it's not all. So, this is the last part of my quick intro about ScyllaDB, and I will be covering some key features of our database. So, ScyllaDB is compatible with both Apache Cassandra and Amazon DynamoDB. Remember in the first slide when I mentioned that we already have too many databases in the world? Well, we agree with that, which is why we decided not to reinvent the wheel and come up with our own query language. Just like RisingWave works with Postgres, right? In other words, if you are already familiar with either Cassandra or Dynamo, you can get started with ScyllaDB in a matter of minutes. So ScyllaDB also auto-tunes itself for your workload. Our system scheduler automatically adjusts the priority of internal database operations, such as compactions, to ensure that those background operations never harm your workload latencies, which is what matters to you. Users also have the flexibility to assign different priorities on a per workload basis. So you are able to interact with our systems scheduler. And by doing that, you can, for example, assign a real-time workload, which is very latency sensitive, and assign higher priority than another workload, such as an analytical one, which you don't need to serve traffic with lower latencies. This is really nice because it helps with infrastructure consolidation. The next feature I want to talk about is tablets, and we even have a video here which you can watch while I'm talking. So tablets is a new feature which we recently introduced, and the main idea is to bring elasticity to the realm of databases, allowing you, for fast topology changes and immediate request serving as you are adding nodes to your cluster. And why those features are important? They are critical when you work particularly with spike unpredictable traffic. And I do have actually a very recent example to give you. So I am not sure if you guys are actually following the news, but I live in Brazil. And one of the things that happened just last week is that Brazil banned Twitter or X countrywide. And because of that, many Brazilians actually shifted to a different social network called Blue Sky. And as a coincidence, it happens that Blue Sky uses ScyllaDB under the hood. And because of that massive migration from Brazilians from Twitter to Blue Sky, they ended up hitting almost 10x traffic in a matter of days. And ScyllaDB was there to support them. All right. So previously I have shown numbers about ScyllaDB, comparing ScyllaDB versus Memcached, and it is no surprise that our latency numbers are actually very low, even on a similar level of throughput. And this is because ScyllaDB actually implements its own cache. So and given our shared notching approach, as you can see in the picture here at the bottom, each CPU core actually has its own dedicated cache layer, which is really cool, and it's really nice to keep cache locality. All right. Finally, the last feature I want to talk about is about change data capture, which is more in line with what Tao and we are going to be discussing today. And I believe Tao is going to speak about syncing data from RisingWave to ScyllaDB, right? But there's nothing in theory that could prevent you from sourcing data from ScyllaDB and storing it on RisingWave. So you could integrate Kafka and source data from Kafka and then sync to RisingWave, or you could use directly our CDC drivers to directly ingest data to RisingWave if you'd like. All right. So this is what I wanted to show. Really quick intro. I hope it wasn't boring. So if you would like to learn more about ScyllaDB, visit our website at scalability.com. And we are available as a cloud offering, an enterprise solution, and of course, also as a free open source offering. All right. So this is what I had to present. If you want to stay tuned with our social media, and a few events for you guys to follow along if you are interested. Late in October, ScyllaDB is going to be hosting P99Conf. I know RisingWave previously spoke at P99Conf, so if you would like to also learn more about RisingWave, there are many talks about talks from RisingWave on P99Conf. But if you've never heard about P99Conf, it's basically an online and free virtual event from engineers and by engineers. And this year, we are going to find companies like Meta, Red Hat, Netflix, Uber, AWS, and more, just to name a few. And they will be discussing all the things related to performance. Later this month, if you never used ScyllaDB, you don't know how to get started and you need some assistance, we will host ScyllaDB University Live, which is an instructor-led event for those of you interested in getting your first touch with ScyllaDB. And finally, if you want to talk with me in private, you have my bit.ly here, bit.ly/ScyllaDB-Felipe. And so, yeah, feel free to book a meeting with me. I'm more than glad to discuss about your particular issues and how we can help. All right. So this is what I had to present. I will stop sharing now. And with that, I guess I will hand it over back to you, Tao.
Hi, thank you for your great talk. And let me share my screen for my slides. All right. Can you see me?
Yes. Okay. Perfect.
So let me start my talk. All right. My name is Tao, and I'm the product manager at RisingWave. And today I'm very excited to share with you today's topic, RisingWave and ScyllaDB. So let's start with a quick introduction to RisingWave. So about 3 years ago, when this project first started, we frequently heard people frustrated with the challenges that they faced when running and maintaining stream pipelines. And it was clear that there was a gap in the market. So we created RisingWave to address these pain points. So the first challenge we found is usability. So existing streaming systems in the markets often use a custom system dialects that's tailored for streaming. Although these SQL dialects are indeed suited more for streaming semantics, they also introduce a steep learning curve for users who are not familiar with streaming concepts like watermark. Not everyone is a streaming expert after all. So we then designed RisingWave to lower the learning curve by offering Postgres compatibility, which allows the traditional database user to quickly build a streaming application without taking a 7-day online training course. So for example, if you search Flink online courses on Google, you will find plenty of them. These courses are great resources, especially if you are a beginner to Flink SQL. But do we really want users to be in a position where they have to take a course before they can start using it? Absolutely not. So RisingWave top one tenet is that users run streaming is just like how they run traditional SQL queries. Of course, RisingWave also supports some streaming specific features like watermarks, but they are not mandatory. RisingWave leverages its decoupled architecture to trade off peak performance for ease of use. So I will explain this in more details in later sections. So the second challenge that we found is cost effectiveness. We found that traditional streaming architecture often tie storage and compute together, which can become very expensive when dealing with large amounts of internal streaming states. So for example, these architectures, these systems might bundle one CPU with 50 gigabytes of local storage. That means that if you have 500 gigabytes of data, you are forced to scale up to 10 vCPUs. So even if you don't need that much of computing. As a result, users often have to apply various optimization techniques to reduce the size of data they store. this entire optimization will add much complexity to the overall pipeline. So look at this pricing calculation of AWS managed Flink. If you need more storage, you have to pay more for KPU, which means one CPU core. A RisingWave solution is to employ a decoupled architecture. It's a separation of compute and storage. Since object storage is incredibly cheap nowadays, RisingWave algorithm tends to leverage more storage to reduce the capacity exposed to users. We will dive in deeper into these details in later sessions. So what are RisingWave's standout features? First is the ability to process real-time data on the fly. RisingWave does not intend to beat traditional databases in benchmarking tests, especially those tests that focus on querying historical data. Instead, we aim to extend the capabilities of traditional databases to tackle a broader range of problems, like a streaming ingestion from Kafka and CDC, or streaming materials field to process event that just occurred seconds ago. Also, you can query the materials views as soon as it's ready, and you can create indexes to accelerate the query speed. The next is scalability. RisingWave's architecture is designed not just to save costs, but also to handle use cases that previously struggled due to scalability limitations. Traditionally, streaming systems like Flink often assumes users are streaming experts. They assume users are knowledgeable enough to deal with deletes themselves. However, we see this as a disadvantage due to the inability to handle deletes in a scalable and cost-effective way. For example, joining multiple sources into a wide table traditionally involves complex watermarks and temporal joins to make sure the output of stream is append-only. As you can see, RisingWave join syntax is written completely in the standard SQL without using special syntax to handle deletes. Under the hood, RisingWave maintains a result table that efficiently handles deletes, and this is essentially similar to traditional databases like Postgres. The overhead is relatively small because most of the cost lies in storage. And RisingWave tier storage is designed to be cost-effective. So in general, RisingWave scalability not only benefits the performance, but also brings huge advantage to usability. But what really set RisingWave apart is Postgres compatibility. With the PostgreSQL interface, RisingWave can integrate effortlessly into existing data ecosystems like BI and monitoring tools, pipeline management tools via the Postgres protocol. And thanks to the vast knowledge base of Postgres in current AI LLM models, even RisingWave beginners can leverage ChatGPT to write nearly 100% correct SQL queries with minimal efforts. And now let's talk about the engine. RisingWave's architecture is built around the separation of compute and storage, which we call tiered storage. It uses object store for persistence and uses a memory index for local caches to speed up the I/O. By using S3, RisingWave technically has no limits on storage capacity. Users no longer have to compromise on data retention and delete their valuable historical data older than a few days. With RisingWave, they can retain data for 6 months or even forever, because under the hood, RisingWave uses a very cheap object store. It's rely on a very cheap object store. This is a 10x improvement compared to traditional systems. This separation also allows for independent scaling of each layer, enabling RisingWave to scale up and down and recover from failures more quickly. In real world, the recovery often takes less than 10 seconds. If you worked as a system admin, you will know what I mean. RisingWave stream processors are built on the state store tailored specifically for streaming semantics. It's highly scalable, as I just explained. It delivers eventual consistency guarantee. It is optimized for fast point lookup and frequent writes. This design makes it ideal for streaming workloads, especially when joining multiple streams into a white table. In fact, RisingWave has been tested to join even 50 plus of streams without encountering any performance issues. Also, users can cascadingly create materialized views on top of materialized views, eventually building a complex stack of real-time data models. RisingWave also supports a broad range of Postgres functionalities, including those originally designed for batch processing, such as over window. Implementing over window in streaming, especially specifically in incremental processing, is extremely hard. Unlike traditional databases, RisingWave processes data not only at read path, but also at write path. This means that every SQL operator in RisingWave comes with two implementations, one for batch queries and one for materialized view queries. Now, materialized view queries, which is based on incremental processing, often requires significant state management under the hood. This process typically is typically harder to optimize. And in fact, many streaming systems often decide to pass this complexity directly to users so that its implementation can be made simpler. But RisingWave is different. Let me show you what it means with a simple example. This SQL very materialized view filters tweets posted in the region one day. And this might seem pretty straightforward in the context of batch processing, but it's not as simple as it looks when it comes to incremental processing. Under the hood, RisingWave maintains a one-day state and automatically discard data older than 1 day. This process does not require manual configuration from users. Now, if you would try this in another system like FlintSQL, it wouldn't be so easy. To achieve the same result, you will have to use Flint's state TTO API or define the watermark on a column of the table. Both of these approaches involve a lot of effort and complexity and a deeper understanding of the underlying systems mechanisms. So with RisingWave, we are not just talking about supporting PostgreSQL or implementing those SQL operators. We're talking about a system designed to simplify the user interface, the user experience. We aim to hide the complexity, not shift it to users. So this allows you to work on reading methods, building streaming applications, and let RisingWave handle the heavy lifting. Oh, and by the way, RisingWave's engine is implemented in Rust, so it ensures that the entire system has a high efficiency in terms of memory use, and it also reduces the possibility of memory leaks. So now shift our focus to ScyllaDB. ScyllaDB itself is high frequency ingestion. Its performance outperforms traditional transaction databases like PostgreSQL. ScyllaDB achieved this feat by making some clever trade-offs. It sacrifices strong consistency for eventual consistency, and this allows it to handle massive concurrent writes. And this makes it perfect for scenarios where data freshness is important, but absolute consistency isn't that critical. So in general, I think ScyllaDB excels in scenarios where high ingestion rates are a must. So IoT data, financial market data, user behaviors, these are just examples of the use cases. But here's the interesting, but many of these use cases require stream analytics running in the background to extract real-time business insights. In IoT scenarios, manufacturing companies can efficiently optimize the production pipelines and detect anomalies in real time. Financial institutes can conduct financial trend analysis on incoming market data, and businesses can adjust their offerings and recommendations based on real-time user behaviors. This is where RisingWave and ScyllaDB form perfect partnerships. RisingWave provides a complex real-time analytics capabilities, and while ScyllaDB handles high-speed ingestion. RisingWave also makes it super easy to join multiple data sources for further analysis, such as building a 360 customer profile, so that you can join offline files from S3, event stream from Kafka, or CDC sources from databases like Cassandra, ScyllaDB, PostgreSQL, and MySQL, all in real time. As Felipe just mentioned, RisingWave is able to consume the CDC events from ScyllaDB via Debian and Kafka, and this entire process is very smooth. So first, we will set up Debian Kafka, and Debian will extract CDC events from ScyllaDB and feed JSON event, feed this format this event in JSON and fed it into Kafka. RisingWave will consume from Kafka, and then materialize this data in the table, in the built-in table. But the integration doesn't stop here. RisingWave also allows you to sync data back into ScyllaDB. This is idea if you have existing pipelines that already rely on ScyllaDB for querying. Instead of rebuilding everything from scratch, we can simply export data to ScyllaDB. This avoids the need for application to modify their code. And the above stated RisingWave plus ScyllaDB pipeline can unlock other exciting use cases as well. For example, alerting. We can run complex monitoring rules on RisingWave, triggering alerts to downstream applications. And empirically, it's not uncommon to see one tenant of RisingWave running thousands of monitoring rules simultaneously. And RisingWave also enables the creation of real-time dashboards because it's Postgres compatible. You can connect tools like Metabase, Superset, Cube.js, or Grafana directly to RisingWave. This allows data engineers to quickly build their dashboards. Okay, this all of my talk, and thank you for your time. So if you're interested in RisingWave, you can start our GitHub repo, and you can visit our official docs, and you can take a look at our YouTube and Twitter. So yeah, thank you very much. Maybe I should hand over to Giovanna.
I think you're muted, Giovanna. We cannot hear you.
That happens all the time. Thank you, Felipe.
Yeah.
Thank
And
you.
that's the good thing about doing live webinars, right? It's real.
Happens. Always happens. And thank you both for your presentation. We have some questions. So yeah, let's start maybe with the first one. I think that's
may I interrupt you for a second? I before we actually start with the questions, we are of course going to address them. But I really liked your presentation, Tao, and I could easily see how both our presentations really had this synergy, you know. So basically, as you said, we both chase extreme performance. We aim to reduce costs and effectively provide unlimited scale to organizations, right? And even beyond that, how it is, right? Without introducing complex, anything complex or hard to manage in an infrastructure. So a few things that I really liked on your presentation is that you spoke about Rust, really nice, and ScyllaDB is currently in C++, and the reason is because when we started, Rust wasn't yet mainstream, but yeah, Rust is definitely awesome, and it's safe, right? So it's a really good chingy, but I think before we actually start with the Q&A, I think one of the things we may want to first clarify is what is the main difference between a streaming database and a database, no LHP database like a regular database like ScyllaDB? I mean, if people aren't yet, if they don't know yet, how would you address this question?
Well, the key difference, the ability to run streaming pipelines. So regular database only process data using they can only do batch processing. They cannot do incremental processing. They cannot maintain incremental states just within the database. Previously, you know, in the Postgres ecosystem, there is a popular extension called PG-IVM, which means that incremental view maintenance. But you know, this is in just an extension. It's not, you know, built-in Postgres. And what we are doing is to provide the capability for PostgreSQL to incrementally process the SQL query. And as a result, the user will be able to, you know, query a very complex query to get the results of a very complex query in real time, just literally in real time, just like in a few seconds.
And also aggregate streaming data, basically, right? Aggregating input sources as they come in. I think that's super cool, and that's exactly the synergy, right, between RisingWave and Scylla. For example, ScyllaDB is a NoSQL database, as you said yourself. We do have some trade-offs. For example, aggregations, running complex queries. ScyllaDB cannot do that because those have been our sacrifices. This is exactly when RisingWave can come in. So if you need to run those complex aggregations on top of your stack, then of course you should be using something like RisingWave to quickly get you the insights you need, right? Does that make sense?
Yeah, indeed. Yeah, and when it comes to very high-speed ingestion, I think users should consider scalability as well.
Yeah, no, definitely. So I just wanted that context.
Now I'll need to interrupt you because we have a lot of questions.
Great.
Yeah. Please, guys. So the first one, you can also open your Q&A tab. The first one I goes to Felipe. What are the performance benefits of using ScyllaDB for large-scale real-time applications compared to other NoSQL databases?
Oh, that's a really good question. Yeah. So I kind of touched on it during my presentation, but it's basically the idea that you can get high throughput with predictable low latencies. And compared to other databases at a fraction of the cost. Because let's be honest, I mean, if we all sit down here and we start comparing any database again versus any database, you can probably get good performance with any database. But I think how much will it cost you to get low latencies? With ScyllaDB, I mean, with a 3-node cluster, you can, depending on your workload, of course, it's not applicable to everyone, but with a small 3-node cluster, you can get to 1 million operations per second. That's impressive. And we do have lots of material in our website showing you and demonstrating how you can achieve that. All right. So predictable low latencies in single-digit milliseconds, high throughput, no latency variability as you go, right? So of course, latency may fluctuate a bit, but it's not like, hey, my latency is 2 milliseconds and then boom, it's now 50 milliseconds. What happened? Okay. So I hope this addresses your question.
It does. Let's move to the next one. Felipe and Tao, could you each explain how the storage layer in ScyllaDB and RisingWave works, particularly with LSM trees? I'm curious how ScyllaDB's use and LSM trees benefits performance and scalability, and how RisingWave's Hammock storage leverage them for stream processing and system efficiency. It's a kind of common between both ScyllaDB and RisingWave.
Yeah. Well, maybe I can talk first. Well, RisingWave choose to use LSM basically because the underlying storage uses S3. So when it comes to S3, we don't have many choices. So in order to store files in immutable data stores like S3, we have to use LSM because LSM. One of the key characteristics of LSM is that its file is immutable. Yeah, so that's how we made this decision.
Good. And for ScyllaDB, basically, LSM trees make sense because, as Tao said, they are append only. And because of that, we are basically can have pretty much unlimited write scalability. So one of the problems with traditional regular databases which follow a B-tree orientation is that every write needs to, an in-place update because you need to either create another node or you need to update a leaf. And because of this operation, writes do not scale as much as when you use an LSM tree. This does introduce some trade-offs. For example, you need compaction in order to optimize your data later on for reads. But I mean, we have tons of users even using ScyllaDB at scale for really heavy workloads. So.
Thanks, Felipe. Another one from Pratik. Can you talk about how does RisingWave's architecture handle back pressure when there is a mismatch in data ingestion rates between Kafka and ScyllaDB? Now?
Well, Actually, I'm not understand this question actually. So maybe for this attendee, they can could you elaborate more?
So Pratik, if you're online, if you can just clarify this question. So let's move to the next one. Felipe, someone saw those plushies behind you and they're wondering.
Yeah, so how do you get one? I mean, get in touch with me. You can find me on social media, and then I can get you in touch with our marketing personnel so they can ship you one. I can't promise if you are going to get one, but I can try to help you with that. And thanks.
Okay. How does the integration of RisingWave streaming and ScyllaDB's real-time data store enhance scalability for growing businesses?
Well, actually, I do not understand this question, but for the previous question posted by Pratik, well, for RisingWave, we handle the back pressure by a queen mechanism between internally. So basically, when the internal queen has too many events, we measure the number of events within the queen, and when the queen size is larger than the threshold, then we will back pressure the the queen between actor and actors cascadingly into from the destination to the sources, and eventually we will pause the stream when the pressure is too high. Yeah, so this is basically how it works.
Can I address the other question?
Yeah, sure. Go ahead.
Yeah. So just to remind the audience of the question is, how does the integration of RisingWave streaming and ScyllaDB's real-time data store enhance scalability for growing businesses? This is basically another way to ask, if I'm starting a company, or if my company is growing, still growing, does it make sense for me to use RisingWave and ScyllaDB at all? It's a really good question. So typically, when you are still scaling, you are on the early stages, you typically need to make a solution, a decision. You can either start with the common stack, which is typically Postgres, a Kafka. You start simple, and then you scale as you go. And then once you hit a specific scale, that's the moment when you say, oh, okay, now I need to re-engineer and re-architect my entire application and my entire infrastructure in order to handle this load. Or you already start doing this work from the ground up, so that when you get to this scale which you are after, you already know you have a solution you can trust, and that won't give you a headache, and you won't need to revisit in the future. All right. So that's how ScyllaDB and RisingWave can help growing businesses.
Now, do you have any thoughts on this?
No, I think Felipe's answer is very great.
Okay, cool. Okay, any other questions? If not, I want to thank you both. Yeah, no questions. So I want to thank you both. And thank you everyone for attending. See you next week.
Thank you, guys.
Thank you, guys. See you.